And well, everybody in this room knows the importance of factorization by now, and let me remind you that in particular, let's say for simplicity that we're on the unit circle, if we introduce the class W of absolutely convergent Fourier series, which is an algebra, the so-called Wiener algebra, that's why W, then there is a very simple and beautiful criterion for the factorization existence, namely a function f from this algebra is factorable if and only if it is invertible. And invertibility can be understood in the sense of invertibility in this algebra, which is the same thing as simple invertibility as being different from zero everywhere. And moreover, the index of factorization is the same as the winding number of this function f. And the factors, so the factorization looks as f being the product of three multiples, f plus times the middle factor, which I will denote by d, times f minus. In this particular case, the factors which are supposed to be analytic inside and outside, on top of that, they are automatically also elements of the algebra. That is, f plus and its inverse are in W plus. These are Fourier series, absolutely convergent, with only non-negative terms present, and f minus respectively with its inverse being in W minus, well, naturally, absolutely convergent Fourier series with only non-positive exponents present. And d in this particular case is t to the power kappa, kappa being an integer, and this integer is the winding number, as I said. So it is as good as it gets in this particular case. Slightly more subtle is the situation when your function f is continuous. Then what happens, the factorability criterion is still exactly the same, but now there are some peculiarities about the behavior of the factors. So it's still factorable if and only if invertible. So basically the same criterion, but now, as I said, the multiples are not necessarily continuous up to the boundary. They are slightly worse, but, well, they are analytic together with their inverses, and the winding number still makes sense, and it's still the same as the index of the factorization. And all the questions concerning integral equations or Riemann-Hilbert problem can be answered in terms of these factorizations. The situation gets still a little bit more complicated when we move to piecewise continuous functions. Then, for better or worse, the criterion is different, but there is still one. Invertibility is still necessary, which, by the way, is a general statement. This is true for all functions in L infinity even. For factorability, it is necessary that the function is invertible, but it's not sufficient anymore. What happens is that factorable is the same as invertible plus. Plus what? Well, invertible in this case means that the values are different from zero everywhere, and on top of that, the function being piecewise continuous, by definition, if you wish, means that there are one-sided limits from the left, from the right. They also have to be different from zero. And here is the additional condition. When you divide one-sided limit by another at the same point and take the argument of this thing, this argument should be different from 2 pi over p. What is p, you may ask now? The thing is that factorability now is a property associated with a certain space. We are talking now about, well, factorability which matters for, say, Fredholm properties of the respective Riemann-Hilbert problem or Wiener-Hopf equation, and that has to act on some space, and this space for this, in this particular case, is LP, and this P is from there. And it has to be between 1 and infinity strictly, because then and only then the singular integral operator with Cauchy kernel is bounded. Okay, well, the winding number is then a little bit more difficult to define. What happens is that you draw a picture again. Here are this is the graph of your function, and there are some jumps. And at each jump point, what you do is you connect the values at the left and at the right by a certain circular arc. The arc from which the line segment connecting these 2 points is seen at exactly this angle. So this is what you do. I'm not sure how visible it is, but these are those circular arcs. And as it happens, this condition is exactly, meaning that 0 does not lie on this curve. And then this curve has the winding number with respect to the origin, and this winding number is the index. And now the picture depends on p. For some p you may be factorable, for some other p you're not factorable, and the index depends on these values. No almost periodic functions yet. Okay. So this is the situation for certain classes of functions in the scalar setting. We all know that it is also important to consider the factorization problem in the matrix setting, and from some previous lectures, in particular from lectures by Frank, we already know also that then situation becomes more complicated for a reason that there are no formulas, at least most of the time, explicit formulas for factorization. In order to find the factorization, you need to take the log, then split the function, then take the exponents. This is all doable in the scalar case, but definitely not in the matrix case. In place of the index, there are now partial indices, and as opposed to the index, partial indices are not stable, and this is another complication. So there are differences. But I don't want to concentrate on these differences now. I want to do quite the opposite. I want to emphasize the fact that as far as existence is concerned, there are no differences, at least in these situations. Everybody can guess the answer by just looking at what happens in the scalar case and state, well, almost state the respective result in the matrix case, and this will be a correct statement. The proof might be more involved, but the statements hold. In particular, I'll try to make the changes as we go. So which color is more visible, blue or red? Any, okay. All right, so if you are in W in the matrix case, still factorable is the same thing as invertible. Invertible, of course, now means invertible as a matrix function, so the determinant has to be different from 0, and this factorization still holds. F plus with its inverse is now a matrix function, but still entry-wise in the same algebra. Similarly here, And in place of this one scalar multiple, what you have to use is the diagonal matrix function with such expressions on the diagonal. As I mentioned earlier, these kappa j are now partial indices. And the sum of these partial indices is the total index, and this is the winding number of the determinant. Continuous, same exact criterion, same exact formulas. F plus and F minus are not necessarily continuous up to the boundary, but still relatively nice. Piecewise continuous, factorable is the same as invertible plus this additional condition. Well, you can make sense of this ratio. You can multiply one matrix by the inverse of the other. You have to choose in what order to multiply, but as it happens, it doesn't matter. Because you are not taking arguments of the matrices, I don't know how, what you are doing, you are taking arguments of the eigenvalues of these matrices. And these two matrices, which differ by the order of multiples, are similar. Therefore, the eigenvalues are the same, and this part remains exactly the same. There is no such nice picture. There is something else, but still there is a formula for the total index, and the partial indices are more involved. This is all very well known. I have not mentioned any names. I should have probably. This is all Simonenko, Gochberg, Krupnik. Okay, now what? Now we want to move to the almost periodic setting. Why? For two reasons. Well, this is about putting pure math and applied math together, right? All this. So the pure mathematical reason is just because it's an interesting question. This is yet another class of functions or matrix functions. The more applied reason is that, well, I can see Christina now in the room. I'm very happy to do that. You will not hear anything new. I'm sorry about that, but you will hear some of your results as well. The factorization, the Wiener-Hopf factorization arose as a tool for solving Wiener-Hopf equations, in particular convolution type equations on half line. As it happens, when solving convolution type equations on finite intervals, factorization of almost periodic functions comes into play. And it is indeed about matrix functions. Even when you start with scalar equation, you end up with a 2 by 2 matrix function. So that's another reason to study these things. So the scalar case first. Well, I need to explain what almost periodic functions are. The simplest almost periodic function is actually periodic. It is simply the exponent, and we will denote it by e sub lambda. And e sub lambda of x is nothing but e to the power I lambda x. Lambda is a real parameter, and this is, as I said, a periodic function with a period 2 pi over absolute value of lambda. And you can consider all such functions, take their linear combinations, finite to start with, and this is what is called almost periodic polynomials. So f being equal this, by definition, is an almost periodic polynomial. And these almost periodic polynomials are not necessarily periodic anymore, because if you have at least two summands and the ratio of lambdas is irrational, you do not end up with a periodic function. But still, there are some properties inherited from exponents, and that's what makes them almost periodic. Now, almost periodic polynomials form an algebra, because when you multiply two exponents, you end up with an exponent. This algebra lies in L infinity. We are now on the real line, by the way, but the transition from a circle to the real line is just a technicality. So, as I said, it is a subalgebra of L infinity on the real line, not closed in L infinity. You may close it. You may close it using different norms. Well, let's consider two of them. If you close it using the norm W, which is simply the sum of absolute values of the coefficients, what you end up with is APW, the algebra of almost periodic functions with absolutely convergent series like this. And this is an analog, as you can guess from definition and from the notation. This is the analog of W. And if you close it with respect to the uniform norm, then you end up with a larger algebra, AP, which is the algebra of all almost periodic functions in the Bohr sense. Well, here is the situation as far as factorization goes in the scalar case. It is very similar to what's written here. For APW, the result is as for W. For AP, the result is as for C. That is, well, I don't even need to rewrite anything yet, or maybe I will. So, F from APW is factorable. I will have to clarify this somewhat. If and only if this F is invertible, and it doesn't matter where, because it all means the same thing, invertible as an element of APW, or invertible as an element of L infinity, or simply different, bounded away from zero on the real line. This is all the same thing. And the factorization has this same form. That is, F plus and its inverse are in APW plus. And I erase with what? Here it is. No. F minus and its inverse are in APW minus. What are these two classes? Naturally, they are subalgebra of APW. Each function from APW, as I said earlier, is simply such a series with possibly infinitely many terms, but the sum of absolute values convergent. So APW plus consists of such functions where lambda j are all non-negative, and APW minus consists of all such functions for which lambda j are non-positive, and they are subalgebras of APW. And this is all very similar to W plus and W minus. Something has to be said about D. D cannot be like that anymore because this is not an almost periodic function to start with. What D is now, well, before I say what it is, let me insert some words of explanation here. This t to the power kappa is a multiple which absorbs the winding of the function f. And the fact that f is winding around the origin actually does preclude the log of f from being a continuous function. And if you extract t to the kappa from f, what's left, the function with the winding number equal to 0, actually has a continuous log. Well, a similar situation holds in the almost periodic case. That is, if you have an almost periodic function which is invertible, you can, of course, consider a continuous log of this function on the real line, which is defined up to a constant summand, 2 pi something, 2 pi I. But this is not necessarily an almost periodic function. There is no reason why it should be. But there is a deep result, much deeper than in the periodic case, by Bohr, saying that there is a unique value, let's still call it kappa, such that if you consider E minus kappa times f and then take the log of this function, then a continuous branch of this log, then it will be an AP, and if to start with you were in APW, will still be in APW. So this kappa, now real, not necessarily integer, plays the same role for the almost periodic setting as the winding number played for the periodic setting, and it has a name. It is called the mean motion. The existence of this kappa is the Bohr mean motion theorem, and this is exactly what you put inside here as D. So now D is not this. It is E sub kappa, with kappa being some real number defined uniquely by your function f. And the factorization exists. And if instead of APW you consider just AP, a slightly bigger class, not slightly, then still the factorization criterion holds, as it was the case when passing from W to C. The multiples are not necessarily almost periodic anymore, but they have some special properties, and they are analytic respectively in the upper and lower half planes. So this is gone, but something still holds. And not surprisingly, in place of a scalar multiple E kappa, you have now to use D of just D equal the diagonal matrix with what am I doing now? That's too early. So still the same E kappa. So and these are results by Goldberg and Feldman on one side of the Atlantic Ocean, and Coburn and Douglas on the other side of the Atlantic Ocean at the time, and it all happened in the 70s, 1970s, so quite some time ago. So the bottom line here is that nothing really exciting and unexpected happens when passing from the scalar periodic functions to scalar almost periodic functions, and also nothing unexpected happens when passing from scalar periodic functions to matrix valued periodic functions. Are you with me on that? Have I convinced you? Yes?
So what are analogs of partial indices then?
We're getting there. But the analog of the index, which was an integer in the periodic case, is this mean motion, which is a real number in the almost periodic case, in the scalar situation. So what, at some point, Yuri Karlovich and I became interested in the matrix almost periodic setting for some mathematical and non-mathematical reasons at the time. And we expected the following. Number one, to address the question I was just asked, what should, for simplicity, I will now consider only APW. It will make things simpler, and all interesting things will still be happening there. So what should be an analog of factorization in this setting, as we thought at the time, I still think. So let's say we have this matrix J, which is in APW n by n. It is factorable. That's by definition, that's not the criterion yet. By definition, if and only if, well, it's not F anymore. If and only if it's the product of three multiples, G plus, D, and G minus. Since we are concentrating on the W situation, I will require that G plus and its inverse are entry-wise in APW plus, G minus and its inverse are in APW minus, entry-wise again, and D, natural to expect, I think.
Yeah.
Yes?
Since we are emphasizing the difference, maybe you like n by n.
Okay. Well, I was saying entry-wise, but yes, I don't object. And D is the diagonal matrix with these elementary almost periodic functions, E, let's say mu1, E mu2, up to E mu n, where mu sub j, which we will call almost periodic partial indices, are some real numbers. So that's the definition. This factorization is called canonical, of course, when this middle factor is actually irrelevant, when all the mu sub j are equal to 0. And it is indeed true, and this is the result by Karlovich on his own, that the existence of the canonical factorization is equivalent to the invertibility of the respective operator. Toeplitz, Wiener-Hopf, Riemann-Hilbert, that you choose your language, but the fact holds. So this makes, we believe this makes it a useful notion. Whether or not and to what extent the notion of non-canonical almost periodic factorization useful is a different story, which is still subject to, well, discussion. Okay. And what we expected was that it should still be true, at least in this APW setting, that factorable is the same as invertible, which would make consideration of Toeplitz, Wiener-Hopf, Riemann-Hilbert, whatever operators in this situation, well, it should proceed as follows. You check the invertibility. This is necessary. If you are invertible, you write down somehow the factorization. And if partial indices are all zeros, it's invertible. If they're not all zeros, you're not invertible. And if they're all non-negative, it's one side invertible, non-positive, another side invertible, things like that. Well, fortunately or not, this is not the case. And that's actually the main message I want to convey. And if it were a 30-minute talk, I would stop right here and I would consider my mission accomplished. I want to attract attention of those who are not yet aware of it, that this is not true, and this is the first occurrence which I'm aware of when indeed the existence criterion in the scalar case and in the matrix case are different. So once again, for Wiener algebra, for continuous functions, for piecewise continuous functions, for some other classes as well, Douglas algebras, for those who are in the know, these are H infinity plus C, existence is exactly the same in the scalar case and in the matrix case. In the almost periodic case, this is not so anymore. More specifically, factorable implies invertible. This is not because it's almost periodic, this is because it's always so due to Simonenko, but the converse is not true. It's not true even for 2 by 2 matrices. It is not true even for 2 by 2 triangular matrices. Later on today, there will be talk by Sergei about factorization of triangular matrices. I'm not aware yet of the content of the talk, but I assume there will be no almost periodicity there. Yes, and then indeed, well, it's doable then. Easily, not easily is a different story, but here, no. And to finish this part up without details, the criterion is still not known. So we do not know the criterion even when, even for n equal 2 and matrices G of the following form, E lambda 0, E minus lambda, and something in one of the off-diagonal entries, even for such matrices in general, if we do not impose any additional conditions on F, the criterion is not known. Moreover, even when this F has only 3 terms, it doesn't have to be in APW, it can be an APP function with just 3 terms. If we do not impose any additional conditions on the spectrum of this function, we still don't have the criterion for this matrix to be factorable. And let me mention that matrices of exactly this form appear naturally in convolution type equations on finite intervals, where lambda then serves as the length of this interval. And F is somehow related to the Fourier transform of the kernel. So this is of some applied interest, and if anyone here becomes interested, I will be more than happy to discuss further details and think about it. Okay, in the time left, do we leave 5 minutes for discussion at the end? Yeah, okay, I'll keep that in mind. In the time left, I will say something about the situations when there are some results. Let me start with something I like, and which is not, unfortunately, applicable to matrices of this form, but this is yet another situation when things work in exactly the same way for periodic and non-periodic situation. This is what I mean. There is a notion called the numerical range, which we have not touched upon here, so I will remind what it is just in case. It makes sense for operators on a Hilbert space as well, but for our purposes a matrix would suffice. So let's take a matrix, an n by n matrix A. Its numerical range, also known, this W has nothing to do with that W. It's not for Wiener, I don't know what it is for, but it is a standard notation. Sorry?
In German it's Werte for Rad.
I see. Now I know what it is for. Thank you. Yeah, so this is the numerical range, which is also called the field of values, which is also called the Hausdorff set. What it is, you take this n by n matrix, you apply it to a vector x, you take the scalar products with x, same x, and you let x run all over the unit sphere of the respective space. This is a subset in the complex plane. As it happens, well, it's easy to see that this is a connected, compact subset of the complex plane. It is also not that hard to see that it contains the spectrum of A. What is not so easy to see, and this is the famous Toeplitz-Hausdorff theorem, doable, but because of time constraints, I will not, of course, go into that. This is a convex set. And as I mentioned, it contains the spectrum. So if the matrix is invertible, its numerical range should not contain 0. Thus, the converse is not true. But when it holds, when the numerical range does not contain 0, it is of course invertible, and more than that, it is called strictly invertible. Let's use this term, and the claim is as follows. An older result is about, let's say, the continuous setting. If you have a matrix G continuous on the unit circle, and 0 does not belong to the numerical range of this matrix for all the values of the variable, this implies, of course, that G is factorable because it's continuous, so it's an overkill, but not only it is factorable, it implies that it is factorable and all the partial indices are the same, and moreover they coincide with the number of with the winding number of the numerical range, if you wish. So this is an old result, my result, but old, and a newer result by Rabinovich and Babajanyan is that exactly the same statement holds when G is in A, P, W or not W doesn't matter. If this condition holds everywhere on the real line, probably you will have to strengthen it by saying that 0 is bounded away from the numerical range. Then still, you're factorable now in the almost periodic sense. Kappas are now mu's, but it doesn't matter, and they all coincide with the mean motion of the determinant divided by n. So yes, this is the situation when factorability holds, and you can even figure out the invertibility of the respective operator. So I like this result because, well, to my taste, it's a very beautiful result. I may be subjective here, but unfortunately, I don't know any single application of it in the real life, in particular because these matrices are never like that. These matrices, for some values of t, you will have their eigenvalues are the values of this function. For some values of t, repeatedly, you will have them on the opposite sides of 0, and then the numerical range has to contain 0. So that would not work. All the other results I know so far, correct, Christina will correct me if I'm wrong, they all relate to this particular setting, the triangular 2x2 matrices of such form. Well, what can I mention in the time I have left? Probably not very recent results, especially since, to the best of my knowledge, there are no new results since, say, 2015. But some, just to give you a taste. First observation is that these matrices, factorability of them depends only on the portion of f. You write it as the Fourier series, which in this case is called Bohr-Fourier series, so there will be some exponents there in this representation, and those of them which are outside of the interval from minus lambda to lambda, they are irrelevant. So only the portion of the spectrum of f between minus lambda and lambda is relevant. One result in which no surprises happen is when, which is what we call the commensurable case. This is when the spectrum of f lies on a certain grid. Let's say minus nu is the leftmost point of this grid, and then there are, well, equidistant points in here between minus lambda and lambda, on which the spectrum of F is required to lie. I'm not saying that all of them have to be present, but this is the only positions the spectrum is allowed to occupy. Well, here no surprises will happen. The factorization does exist. It can be written down explicitly, and the criterion for it to be canonical is available. I will mention here a particular situation because I hope that maybe it makes some applicable sense for you. So this grid does not have to pass through zero. Zero may or may not lie on this grid. But for the situation which I want to discuss further, it does. So suppose that zero is on this grid, and well, then there are some other points. Then, if lambda, and thus minus lambda, also is on this grid, then this is actually not almost periodic, this is periodic. And you can extract the respective result just by change of the argument, which rolls your real line into the unit circle. And then the result is known, and it goes back to Krupnik and I don't remember Feldman or Marcus, but one of these two combinations, and everybody can derive it by now easily. The result is that the factorization exists if and only if a certain Toeplitz matrix is invertible. What Toeplitz matrix? You take the Fourier coefficients of your function f now, put them in the matrix, and if lambda over this h is n, you keep the n by n block. So something like this. So that's their situation. Our situation is when lambda is not on the grid. But then it is between two such points. The claim is that then we have the canonical factorization if and only if two Toeplitz matrices are invertible. One which corresponds to lambda being here, and the other corresponding to lambda being there. Well, for some reason I want to believe that this result has some mechanical maybe interpretation, but I don't know what, and if anyone can figure it out, I will be grateful. Let's talk about it. So this was one case, commensurable. The other case, which we call a big gap situation, is when there is no periodicity required now. You can have as many exponents as you wish. By the way, commensurability, of course, implies that you have to deal with almost periodic polynomial. You can have only finitely many terms. Now you can have infinitely many, so as many as you wish somewhere to the left, as many as you wish somewhere to the right, but there should be a gap, a big gap, and big means that the width of this gap, d, is at least lambda. Then the situation is as follows. For the factorization to exist, it is then necessary and sufficient that there is the rightmost point of this portion, the supremum should be the maximum, and there should be the minimum of this portion, which of course is satisfied automatically when you are dealing with polynomials, but not in general. And that is the statement from a paper by Kristina, Yuri Karlovich, and myself. I don't remember the year, but 2010 or 11, maybe. And well, and if this condition is satisfied, then the factorization can be found. Corona problem plays some role here. And the partial indices you can compute without doing anything. Here they are, plus minus d minus lambda. By the way, for such matrices, there are two partial indices, and they are, of course, opposite of each other, because the determinant here is 1. And the sum of the partial indices is the mean motion of the determinant. But what they are is a question, and here is the answer. So the canonical factorization happens if and only if this gap is exactly of width lambda. As I said, the result with infinitely many terms is from our paper with Christina. Some partial results in this direction were known earlier, in particular when there is only one point to the left, as many as you wish at the right, or the other way around, and so on. And this also covers what we call one-sided situation. This is when all the exponents, let's say, are non-negative, or all the exponents are non-positive, and it is indeed covered by the big gap scenario, because if, let's say, you have all the exponents non-negative, then your big gap is right here. This is the big gap. And its length is lambda if and only if you have a point over there. So if all the exponents are non-negative, the factorization does exist if and only if there is the minimal one, and this factorization is canonical if and only if there is a constant term, a non-zero constant term, in the Fourier representation of f. Okay, what is the simplest case not covered by these two? Let's think about it. I forgot to mention, but it's easy to see, that commensurable in particular covers binomials. Why? Because if you have only two exponents, the left of them is your minus nu, and the distance between them is your h. So two, they always lie on the grid. So in order to have something not covered yet, you need at least three exponents, and they don't have to be one-sided. Therefore, you need one negative, you need one positive. So let's say your negative one is minus nu, your positive one is alpha, and something in the middle, let's call it mu. What happens here is that if alpha plus nu plus absolute value of mu is at least lambda, this is factorable. Unless mu is 0 and alpha plus nu is exactly lambda. And then what happens is, well, if alpha over nu is rational, this is again factorable because this is commensurable. So we will impose the condition that it is not rational. And if we have this, this is what happens then. And this is the first example which we discovered with Yuri at some point. We didn't know all this theory then yet, but somehow we figured it out. Then everything depends on the coefficients. And it is the first situation when the coefficients do play the role. In all the other statements, it was all about the spectrum. The coefficients were irrelevant. What's happening now is that let's denote the respective coefficients by c minus 1, c naught, and c1. You have to do this. You take c minus 1 by absolute value, you raise it to the power alpha. You take c1 by absolute value, raise it to the power nu. That's one side. Then you take c naught by absolute value, raised to power lambda. And you compare the two expressions. If and only if they are different, your matrix is factorable. And then, automatically, the factorization is canonical. If you have the equality, factorization fails. So this is the first and so far the simplest example we know when the almost periodic factorization indeed may not exist even for matrices of this very simple structure. Well, what can I say in the time left? Two things. Number one, this is not the state of the art, but what I left behind the screen is, well, there are no, well, I don't know if Christian agrees with me or not, but there are no really nice results beyond that. There are several more involved situations where we still can write necessary and sufficient factorability conditions for matrices of this form, and they get more and more cumbersome. And we still do not really know what is behind it, what makes this tick. When does the factorization indeed exist, and when it does not exist? Moreover, in all the examples we know so far, it looks like factorable matrices constitute the majority, because as you can see here, for the factorization to exist, the criterion is the inequality. So it fails when you have the equality. But you can pass from equality to inequality just by a slight perturbation of either of the coefficients. So the set of non-factorable matrices in these examples seems to be nowhere dense, while the set of factorable is, on the other hand, open. However, in contradiction with that, very counterintuitively, we have a paper with Leiber Rodman, unfortunately deceased, and Alex Brudny, where we showed that actually, if you consider the set of all almost periodic invertible matrices and its subset consisting of factorable matrices, even more if you consider the algebra generated by all factorable matrices. It is actually a small subset of all invertible matrices when n is bigger than 1. So the situation is very different from what it is in the scalar case. Yeah. Well, I have 2 more minutes left, but I don't have anything really important to say, so I will stop here.
Thank you. Questions?
When a mathematical problem coming from a physical context has no solution, it usually indicates there was a missing idea in the physical context. Do you know what those ideas are?
No, and this is why I'm here. I want help in figuring out what is missing. So there is something behind the scenes here, but we don't quite know what it is.
Other questions?
Frank.
In diffraction theory, the simplest cases of this type of matrix functions that appear contain an f, is the algebra generated by rationals and square root functions. So particular in the algebra of further continuous functions with 2 different limits at infinity. Can you say something about this special case?
Yes. Well, this is also from our work with Yuri Karlovich. Actually, we can consider matrices not from, this will fill these 2 minutes in, I guess. There is a larger algebra, SAP, which is the class of semi-almost periodic functions. This is the algebra generated by AP, and functions, well, you may consider even piecewise continuous functions, but their jumps at finite points are irrelevant. The important thing is that they are allowed to have jumps at infinity. And the factorization problem for matrix functions in SAP reduces to the problem for AP. So if we can figure out what happens with purely almost periodic functions, then we will have the answer for semi-almost periodic almost automatically. So the main difficulty lies in almost periodic part.
I might try to guess answer on what Michael asked. So I am an applied mathematician. I want to use it.
Yeah.
And I'm asking myself question, so I'm not thinking about factorization, I'm thinking about solution to the Wiener-Hopf problem. I should have solution described in this in the algebra of quasi-periodic function. Probably I would better sit in something what is decaying more clearly, like polynomially decayed and so on, so on. So why I should sit in this particular algebra?
Because they arise automatically, in particular when, say, you consider convolution equations on finite intervals. They appear there naturally.
So this is very, very specific case, exactly. And this is, the case is so specific because there is, when we are speaking about Wiener-Hopf on the half-axis and the finite is completely different story.
Yeah.
But in most of the real life, I would say, when you're applying a guy, so I think you're sitting in something what is not belong to that class of the problem.
Well, may I just add a comment to that? Almost periodic functions are symbols or the coefficients. They're not the solutions. Solutions will still be in LP. They will still be.
Yeah.
Yes,
decaying,
but
etc.
yes,
So
but
it's
in
just
fact, I do not want to. So if you tell me that I will find this solution, with which I need only 2-3 approximated terms to catch the full picture, with only that type of the terms, I'm happy. But if I should increase this to have, I mean, the real solution having 100 terms in terms of 3, it's counterproductive.
Okay, well, we'll talk about it.
Just one quick question. Isn't the space of almost periodic functions what one would consider in looking at a discrete Fourier transform representation of these problems? Because that's the standard numerical approach.
Well, but this standard numerical approach probably hides the peculiarities of the situation, because once again, the factorization may not exist.
Right. I'm saying that this may be relevant to the way that numerically everybody sets everything up all the time if they have to do a numerical factorization. It may live exactly in your space. I was just checking if that's correct.
I don't know.
There's another comment on this problems from diffraction theory. Actually, in basic problems, one can show that it must be invertible, the operator, because of a reasoning coming from
some other
boundary variable problems, you have elliptic problems and all this machinery. And because the problem, the operator associated to the problem is equivalent to this one, then you can say, okay, it's invertible, but I cannot factor it.
Okay, but then you can try to use it backwards and make some conclusions about this from your physical considerations.
Ilya, can you say something about a finite number or convolution equation on finite number of intervals?
Yes, it also can be reduced to factorization of almost periodic matrix functions. They will not be 2 by 2, they will be larger, and they will still have even more sparse algebraic structure. More specifically, there will be non-zero entries only on the main diagonal and in one row.
I suggest we move on. Thanks again. Thank you.